Hello and welcome to this lecture 3 on machine learning. In this lecture, we will more formally talk about linear regression and the least square fit to linear regression and different variants of the same. So we will present some formal definition, setup notations that will help us appreciate linear regression more generally. We'll also consider variants of linear regression, and finally we'll present a least square solution to the linear regression problem and present a geometric interpretation to the same. Now for us, linear regression is only a canonical example that also helps us appreciate many other aspects required for machine learning. For example, optimization. We'll see how we can formally derive the least square solution to linear regression. A very important topic, which is overcoming the overfitting problem. And toward that, we'll present a probabilistic interpretation to linear regression and then a Bayesian estimation for the parameters of probabilistic linear regression. That will also lead us to the more general concept of regularization. We will also discuss nonlinearity that can be attained through different formulation of linear regression. This could be variants both in terms of the error function and also through the regularizer. That will lead us to the topic of kernels, which are basically tools for getting high dimensional embeddings for example inputs, but obtained implicitly through dot products. So more about this later. Finally, we'll discuss non-parametric estimation and also highlight what has been parametric about our estimation so far. So an illustration, imagine that you have some independent variable such as investment into a TV commercial. So you're running a company and you want to know how much to invest into a TV commercial. And what is the output or the dependent variable? It is basically the sales. So is it that higher the investment, more the sales? A company really wants to determine how much to invest based on a desired output level that it targets. So Y star is the desired output level. Please note that we are still trying to predict the dependent variable Y star based on the independent variable, which is X, or the investment into TV commercial. Just that we have presented the problem as slight different flavor, which is we're trying to find the right amount of investment to get a desired level. So our investment still will remain the input variable. But what is the basis for learning such a function f and determining Y star based on X, and also reverse engineering and finding the X to get a desired Y star? The basis is previous observations of the form xi yi. Xi is an instance of money spent on advertisements in the past, and yi was what was harvested as returns. Now, linear regression model, we make an assumption that y is a linear function of x. And as I pointed out earlier, once we have learned y, or rather learned beta naught and beta 1, we could always go back and find x star for a desired y star. The problem of estimating beta naught and beta 1 is precisely the problem of estimation for regression. We'll deal with estimation for several supervised learning problems, regression being the simplest of them. However, when we plot xi's and observe the corresponding yi's, we find that treating the investment as a single value and trying to predict the sales based on that investment might not be a good idea. Especially, it doesn't lead to a very neat linear fit. As you can see here, the linear fit is here, but doesn't look very convincing. Why is it so? Well, we landed up treating our investment as a single number. What about treating the investment as an object? Now, the object could have multiple attributes. I'll call them or denote them by phi. So phi 1 xi could be the date of investment. phi 2 xi could be the value of investment. What I've tried to fit here is yi as a function of just phi 2 of xi, the value of investment. Perhaps I should consider fitting yi as a function of several such phi's. So what does this mean? We are trying to get a somewhat nonlinear function of the xi's, but a linear function of the phi's. So y equals w transpose phi x. Expanding it out, it will mean summation I equals 1 to n wi times phi ix. So weight wi assigned to the phi I, or rather the ith attribute. So my linear regression is linear in w's and linear in the phi, but non-linear or not necessarily linear in the x. And the non-linearity is courtesy the phi. So my phi is a vector, and so is my w. Just recap the example of phi's. So phi 1x could be the date of investment, phi 2 could be the value, phi 3x could be the time of investment, or rather the time of commercial. You could also look at the duration of commercial and so on. So possibly my y indeed turns out to be a linear function of x mapped in this somewhat non-linear space. Well, it's linear in the phi's in the eventual space, but non-linear in the x. So continuing with this notation, the dataset D will consist of m training examples x1, y1 to xm, ym. The x's will be the input or independent variables. The y's will be the output or dependent target variables. We'll try and use j as an index into the training set. So xj, yj is a specific training example. We'll try and use i's as indices into the attribute functions. We'll also call them basis functions. So the phi's could be very specifically designed for a domain, but there are also general classes of basis functions which could be obtained off the shelf. Examples are the radial basis function or the Fourier basis or wavelets and so on. And the general regression problem is to find a function f in some class or space of functions such that you minimize an error. Now the error is what will help us determine the best predictor. So if the prediction with respect to an f is very far from what we observe in the data set, you would incur higher error. One can get more specific and choose a particular class f which invokes parameters w. So for example, f, if it's chosen as a linear class or class of linear functions, will basically be all the w's such that w transpose phi x is fx, or rather w transpose phi x is what should be matched with the dependent observation y. A small note here, as far as linear regression is concerned, we might switch between the use of a bias in the linear function, and often we might even just drop that bias. So the most general setting, we have a linear function f phi x w as w transpose phi x plus b, and as I pointed out, we could drop the b How do we do that? Well, we can drop that b by expanding phi to phi tilde and w to w tilde. Now what is this phi tilde? Phi tilde is nothing but phi, but with a 1 padded at the bottom. W tilde is nothing but w with a 1 padded at the bottom. So please get comfortable with both the use of b and the dropping of b. So with this parameterization, the problem is to determine w star such that you minimize the w, the weight for the linear function. One might also use the b and do an argument over w and b. Now what should be the error function? The error function, or the function to be minimized, could be determined based on what is a good or a generalizable model. For example, we have already motivated the sum of squares error. Where the error function is a sum over all the data points of the desired dependent output yi, and from that you subtract w transpose phi x and square this. So this gives rise to the least square linear regression problem. Now you could consider variants of this where you make changes to the error function or the objective function. Ridge regression is an example where you introduce a shrinkage parameter. It's also called a regularization parameter. So you consider the least square function, but to that you add a component norm w square, the Euclidean norm of w squared, and this is added to reduce discrepancies due to variance. We'll present some very specific details of ridge regression in the following lectures. We'll also present a probabilistic motivation for the introduction of the norm w square. But suffices to say that this gives rise to another class of regression called ridge regression, and this gives you an additional advantage that the models generalize well beyond the training data. More about this later. One could also look at regression where the dependent yi is not necessarily real valued. For example, it could be binary 0 or 1, as is the case with classification. In logistic regression model, the function to be predicted is basically the log of the odds, the probability of y given x divided by 1 minus probability of y given x, the log of the odds. And this is assumed to be a linear function. So in some sense, this is still a linear regression problem, but there is a transformation that is performed on the space of predictions. So what you predict is not based on f directly, but based on the probability. We'll also discuss variants such as lasso regression, where you consider the error function as the least square error, but instead of a shrinkage using the Euclidean norm, you use the L1 norm. More about these later, but this was, I think, a sufficiently representative set of variants of linear regression, and we'll find that these variants also hold for other supervised learning problems. So back to least square solution. We already discussed the motivation for the specific form of least square error. It leads to accuracy and tractability. Accuracy over unsigned variants of the error, because we were interested in errors on either side being penalized. Also, it's easy to solve such an optimization problem, minimize such an error function. So our task is to obtain W star that minimizes this specific form in equation 7. How do you obtain this form? Now we know that if 0 were attained at W star, which means that if error were actually 0, which means that each yi was exactly equal to W transpose phi xi, which means in vector form y equals phi w. We should be able to quickly get the w by inverting phi and multiplying with w, with y. Right, so the basic idea is y should belong to the column space of phi, and in such a setting W star can be obtained. Obviously, phi need not be a square matrix, n need not equal m, and hence we might not be concerned with the inverse of phi. Phi inverse may not exist. So a more mature answer would be that I would solve the linear equation so please verify that dimensions are correct. Phi is an m by n matrix, W is a vector, and we already know the direction of y into the column space of phi. So let us summarize our observation. In the case when y belongs to the column space of phi, or in other words, a solution to y equals phi w exists. All this would mean that zero error is attainable. So what does this mean? This means that you could solve phi w star equals y using your favorite Gaussian elimination. If phi happens to be square, you could invert phi and so on. However, this is often not the case. And the simplest reason is that phi w star doesn't coincide with y for every observation. Or in other words, y is not in the column space of phi. So if 0 were not attainable at w star, that is y is not in the column space of phi, what could you do? Well, what you could do is find a w star or y star in the column space of phi such that y star is as close as possible to y. Now what does that mean? Well, it just means that y star is in the column space of phi and the least square solution is such that the distance between y star and y is minimized. Let's try and visualize this. So when would this distance be minimum? The distance between y and y star. We would expect this distance to be minimum if the line joining y to y star, vector joining y to y star, is orthogonal to any vector lying in the column space of phi. That is, y minus y star should be orthogonal to the column space of phi. Now what is a column space? It is basically the space of all linear combinations of the columns of phi. So this is the same as saying that y minus y star is orthogonal to each column of phi. Now what does this mean? This means that y minus y star transpose phi should be equal to 0. So we have y star equals phi w and y minus y star phi equals 0. I could substitute for phi star from 8 into 9 and get 10. Or rather, the next step, which is phi w transpose phi equals y transpose phi. So with phi w transpose rewritten as w transpose phi equals y transpose phi, and then I would also happily take the transpose of both sides. After all, equating two row vectors is the same as transposing them and equating the corresponding column vectors. That's what we do here. You transpose both the left hand side and the right hand side. Now phi transpose phi is an n by n matrix. It's a square matrix. Recall that phi is an m by n matrix. So one could talk of the inverse of phi transpose phi, and in fact phi transpose phi is invertible if and only if phi has full column rank. All the columns of phi are linearly independent. Now what does phi having full column rank mean? It means all the attributes phi1 to phi n are somewhat independent of each other. You can't express or derive one of the attributes using the others, especially in a linear sense. So the keyword here is linear. Also, it'd be good if no data driven dependencies are induced amongst the phis. So let's get back to the claim about invertibility. So if phi transpose phi were invertible and phi was not full column rank, can we discover a contradiction? And the answer is yes. So if phi was not full column rank, we know that there exists x not equal to 0 such that phi x equals 0. And this would mean that pre-multiplication with phi transpose will keep the 0 intact, which means that a non-zero x leads to phi transpose phi x being 0, that is, phi transpose phi is not full column rank. A contradiction. We can similarly prove the other part. If phi were full column rank and phi transpose phi were not invertible, what would happen? We can discover a contradiction in a very similar manner. So phi transpose phi were not invertible, there exists an x not equal to 0. So phi transpose phi, remember, is a square matrix, so its non-invertibility means it's not full column rank or full row rank, which means for this non-zero x, some non-zero x, phi transpose phi x is equal to 0. Now I can pre-multiply with this non-zero x and get this equality. This quadratic form is nothing but the Euclidean norm square of phi x, and the norm is 0 if and only if the vector itself is 0. So this must hold, phi x must be equal to 0. This is again a contradiction because we assume that phi were full column rank and phi x is turning out to be 0. So we have proved one part of this claim in this slide. We proved that if phi has full column rank, then phi transpose phi should be invertible. So geometrically, we can summarize the solution W star as that which yields Y star lying in the column space C phi, such that Y star is basically the orthogonal projection of Y into the column space. So how about analytically deriving W star? How do we get this? So how to minimize a function in general, or how to minimize our error function to get W star? Is closed form solution always possible? So in some of the coming lectures we'll get introduced to concepts involving optimization or minimization of an error function E of W, often subject to some constraints such that GW less than equal to 0 and so on. So tools such as level curves in surfaces, level curves of the error function, gradient vectors that go from one level curve to another level curve in increasing values of the level curve, directional derivatives, which are basically gradient vectors in specific directions projected on specific directions, and tangential hyperplane and so on will become very handy. And one of the simplest algorithms for helping discover optimal solutions is the gradient descent algorithm. In fact, so-called gradient of the error function E when set to 0 is what gives you the W star that we have derived, or rather motivated geometrically.